Thank you for watching our video. In this presentation, we will introduce our developing code, PHITS. The project of PHITS was started around year 2000. Currently, about 20 team members are working on its development and maintenance, and Japan Atomic Energy Agency is responsible for distributing and promoting the code. Here is the table of contents of this presentation. It will take roughly 40 minutes, and at first, we will explain about the general features of PHITS. PHITS represents particle and heavy ion transport code system, and it can analyze the transport and collision of nearly all particles over wide energy ranges up to 1 TeV, using Monte Carlo method. It is all-in-one package type code. That means all contents of PHITS such as source files, binary, data libraries, graphic utility are fully integrated in one package, and it is available in free of charge by submitting application form via PHITS website. It has been used for various applications such as accelerator design, radiation therapy and protection, and space and geosciences. In this slide, we briefly explain what is Monte Carlo method. Monte Carlo method itself is a general simulation technique that uses random number, and when it is applied to the particle transport simulation, it traces each particle motion using random number, and estimate their average behavior by iterating the simulation. For example, when a charged particle goes into a material in the Monte Carlo simulation, it sometimes causes collision in the material and generates secondary particles. This collision point is determined from the reaction cross-section and random number. These secondary particles are further transported until all particles go outside or stop in the material. This entire process, from the birth of single particle to the death of all its descendants, is called history of a particle. Then, simulation of next history is started. In this time, the particle simply stops in the material without causing any collision. Then, the simulation of next history is started. The behavior of each particle is highly stochastic issue and it does not have physical meaning, but if we iterate the simulation for many times, their average behavior is getting closer to the realistic and has physical meaning. Therefore, Monte Carlo simulation is time-consuming, but accurate when the number of iterations is sufficiently large. It is much easier to show what Monte Carlo simulation is than explain about it. This animation shows the motion of 101,000 photons produced from cesium-137 simulated by PHITS. Blue area is concrete, and it can reflect photons like a mirror because photon is a kind of light. Then, if we take the average of all particle behaviors, we can determine the mean particle fluence and estimate the shielding ability of this concrete maze structure. For example, we can say that this concrete maze has a good shielding ability because only 2 of 100,000 photons can reach to the end of the maze. This slide summarizes the basic features of PHITS. The source code of PHITS is written in Fortran, and you can compile it by Intel Fortran and G Fortran. However, we know that Fortran is rather old language, and not so many young researchers are familiar with. So, the input file of PHITS is written in PHITS original language in free format text, and you do not have to write Fortran program nor even compile PHITS just for running PHITS. Of course, if you are familiar with Fortran, you can use PHITS more deeply by combining it with your own source generation or tally definition programs written in Fortran. The geometry in PHITS is described in general geometry format, so-called GG, and it can be visualized by built-in program named Angel and GUI software named Fig3D. You can also use support software developed by other institutes for visualizing and creating PHITS geometry, such as ParaView and SuperMC. As for tally, you can easily deduce any kinds of physical quantities such as particle fluence, absorbed dose, number of interaction, nuclide yield using built-in tally functions, in the format of text data, histograms, and contour maps. Platforms on which you can run PHITS are Windows, Mac, and Linux, and MPI and OpenMP parallelization are available. MPI is a powerful parallelization protocol, particularly for a computer equipped with a large number of cores such as supercomputer, and OpenMP is a easy-to-use parallelization protocol particularly useful for Windows and Mac PC. So, basically, PHITS is optimized for all kinds of computers. Next, we will talk about the physics models implemented in PHITS. Physical processes included in PHITS can be divided into two categories. One is collision and decay processes occurred at a certain point, and the other is transport process between these events. The former can be further divided into three subcategories, which are nuclear interaction, atomic interaction, and particle decay. As for nuclear interaction, any kinds of reactions such as high-energy spallation reaction, photo and muon-induced reaction, absorption, resonance, and fission reactions can be considered. As for atomic interaction, photoelectric, Compton scattering, pair production can be considered for photon interactions, Mahler-Baba scattering, annihilation, Bremsstrahlung for electrons, positrons and muons, and knockout electrons, so-called delta ray production for hadrons. In addition, each ionization and excitation can be explicitly considered in the case of using track structure mode, which will be explained later. As for particle decay, decay with lifetime for all unstable particles including neutron can be considered. The transport process can be also divided into two subcategories. One is the ionization and excitation, and the other is external field and reflection. As you may notice, ionization and excitation are also categorized as collision process, but in general, they are treated in the transport process because number of their occurrences are so numerous that they cannot explicitly treated in most cases. So, PHITS generally adopts continuous slowing down approximation and energy and angular struggling models to reproduce charged particle motions in materials. Using these models, PHITS can easily determine the energy of charged particles after passing through a certain distance, like 100 MeV. Proton immediately becomes 92 MeV after passing through 1 cm water in PHITS, without reproducing millions of ionization and excitation events. As for external field and reflection, electric and magnetic field, gravity and reflection by supermirror can be considered. The last two items are important only for neutron beam line design. Here is the map of models recommended to use in PHITS. There is no perfect model that describes all interactions caused by varieties of particles over wide energy range. Therefore, PHITS combines several models and data libraries depending on particle type and energy. For example, PHITS uses an intranuclear cascade model named JAM and an evaporation model GEM for simulating neutron-induced nuclear reaction above 3 GeV, and uses another intranuclear cascade model INCL 4.6 for energies between 20 MeV and 3 GeV, and uses nuclear data library GENDL 4.0 coupled with event generator mode below the energy. For nucleus-nucleus interaction, PHITS uses quantum molecular dynamics model JQMD instead of intranuclear cascade model. For electron, positron and photon transport, PHITS uses EGS5, track structure, or EPDL97. Basically, PHITS can transport particle energies between 1 keV up to 1 TeV, except for neutrons and electrons and positron in the cases of using track structure mode. The switching energies between the models can be changed by input file of PHITS, but basically, we set the most appropriate value as the default value, so you do not have to change the values in most cases. In next several slides, we pick up some models and explain about their features. The first one is JQMD, J-PARC quantum molecular dynamics model. It can dynamically simulate the time evolution of nuclear reactions, considering the correlations between every combination of nucleons in the frame. So, it is dedicated to simulation of ion-induced nuclear reaction. Therefore, it can precisely reproduce residual nuclide yields and secondary neutron productions by ion-induced nuclear reactions. Owing to the implementation of this model, PHITS became the first general-purpose code capable of handling heavy ion transport, and we are still improving this model by introducing new features. Next, we will explain about Nuclear Data Library. Cross-sections for low-energy neutrons strongly depend on nuclear structure. For example, these graphs show the neutron reaction cross-sections of cadmium-112 and 113 taken from GENDL 4.0 data library, and you can observe huge resonance peak only in the data for cadmium-113. This is why cadmium can be used as neutron absorber. Physics models such as JQMD are inadequate to describe this difference because they cannot consider nuclear structure. So if we had used JQMD for this calculation, we would obtain quite similar results between these two nuclides. Therefore, Nuclear Data Library evaluated based on experimental data for each isotope is necessary. In the PHITS package, Japanese evaluated Nuclear Data Library GENDL version 4.0, which contains neutron cross-sections below 20 MeV for 407 isotopes, and its high-energy extended version, which contains neutron and proton cross-sections below 150 MeV for 25 isotopes, are included. More information and data are available from these websites. Next, we will explain about Event Generator Mode (EGM) and unique function of PHITS. EGM is our original sampling method of secondary particles using Nuclear Data Library. It samples all secondary particles from two-dimensional energy sampling space at once, considering energy and momentum conservation in an event. You may feel that it is obvious because it is a nature of Monte Carlo simulation. However, if you use conventional method, it samples particle by particle from one-dimensional energy distribution. Therefore, the energy and momentum conserve only in average, and not in event by event. For example, it sometimes picks up two high-energy neutrons or two low-energy neutrons from one reaction. In most cases, the energy and momentum conservation in average is sufficient, such as shielding calculation, but it is indispensable in some cases such as detector response and soft error rate calculation. Next, we will explain about track structure mode. In the default setting, the energy loss of charged particle in PHITS is simulated using continuous slowing down approximation (CSDA) that combines a number of ionization and excitation as an event. However, this approximation is not precise enough if you want to simulate particle trajectory in nanometer scales such as DNA. In that case, you have to use track structure mode that explicitly treat each ionization and excitation as an event. This animation shows the trajectories of carbon ion with 5 MeV per nucleon simulated by CSDA and track structure mode. As you see, complicated trajectories can be reproduced by the track structure mode. This mode is very useful for applying PHITS to radiation biology such as DNA damage estimation. Of course, these physics models and libraries implemented in PHITS have been well verified, and their comprehensive benchmark results are published in an open access paper. In most cases, PHITS can reproduce experimental data very well, but some cases are not, such as fission yields as shown here. So, if you want to know how accurate your PHITS simulation is, please check this paper. In addition, all input files used for these benchmarks are included in the PHITS package. Next, We will introduce the applications of PHITS, and the first application is the design of radiation facilities. There are several useful functions for facility design. For example, PHITS can use variance reduction techniques for reducing computational time based on weight window generator and cell importance methods, and PHITS can consider various kinds of electromagnetic fields such as dipole and quadrupole magnets, wobbler magnet, parallel electric field, and complex field map defined in XYZ or RZ coordinate. In addition, PHITS is capable of direct calculation of operation and protection quantities such as H*10 and the effective dose, sensitivity analysis of a certain parameter based on ANOVA, estimation of the time evolution of induced activity considering decay chains of radioisotopes, phase space source based on RMS emittance, and coupling with thermal analysis such as PHITS plus ANSY's fluent like this figure. One of the most important applications of PHITS is the design of J-PARC facility. J-PARC represents Japan Proton Accelerator Research Complex, and it is constructed into a chimera as the joint project between JAEA and KEK. It consists of several proton accelerators with energies up to 30 GeV. It is used for various purposes such as particle physics and neutron generation. These pictures show the 3D geometry view and flux distribution around COMET experimental facility, which searches for coherent neutrino-less conversion of a muon to an electron. It bombards 8 GeV protons to the target and generates pions and muons, and some of them are guided to the experimental room using bending magnet. PHITS has been also used for the design of neutron beam lines in material and life science experimental facility in J-PARC. In this facility, 3 GeV protons are hit on Mercury target for generating neutrons, and they are guided to experimental facility via 23 neutron beam lines. These pictures show 2D and 3D geometry views and dose distribution around a neutron beam line. For this simulation, we prepared several special functions, such as duct source option, which is a special variance reduction technique for long beamline, and consideration of mechanical and optical devices such as multiple magnets, T0 chopper, and supermirror, and even gravity can be considered because cold neutrons gradually go down to the ground direction. Next application is to the design of RI beam factory, which was constructed by Riken for accelerating various unstable nuclides up to uranium. Nihonium was discovered in this facility. PHITS was used in the shielding design of this facility, particularly around in-flight RI beam separator big rips. In addition, PHITS was also used in the activation calculation around beamline by estimating the yields of RI generated by uranium beam. The function to plot the yield distribution on the nuclear chart is useful for this calculation. Next application is to the design of Tokamak fusion device. Accurate prediction of heat, defect, and activation in complex Tokamak fusion device is indispensable for its design. PHITS has been used for the design of Tokamak fusion device JT60 and calculated the neutron fluxes in the vicinity of device with and without considering shielding effect. As you see, shielding is quite effective in these cases. Of course, PHITS has been used in the design of many other facilities, such as Fukui Prefectural Hospital Proton Therapy Center, CT Room in Kyushu University Hospital, and J. Karen Laser System in QST Kansai, and some of these data were used for getting the permission from Nuclear Regulation Authority in Japan. Next application is to radiation therapy and protection. PHITS has various useful functions for medical application too. For example, PHITS has RI source generation function that can reproduce the decay of any RI with or without considering its daughter nuclide contribution, based on ICRP 107. Voxel and mesh phantoms, which represent fine structures of human body by repeated volume pixels, so-called voxel, or tetrahedral meshes, can be easily used in PHITS. In addition, special algorithm to reduce the computational time of particle transport in tetrahedral mesh was implemented, so use of mesh phantom is faster than that of voxel phantom, which is a unique feature of PHITS. As for microdosimetric function, special tally named TSED is implemented for calculating microdosimetric quantities such as lineal energy, Y, and the specific energy, Z, without performing time-consumptive track structure simulation as described before, and this function is useful in dosimetry for particle therapy. The last one is the phase space file convert, PSFC, for PHITS, which can automatically convert phase space source information compiled by IAEA to PHITS source format for simulating medical accelerator beams, without reproducing the confidential information such as accelerator head. Using some of these functions, we developed radiotherapy package for PHITS, so-called RT-PHITS. It can convert not only DICOM image and plan data to PHITS input such as a voxel phantom and source section, but also dose distribution calculated by PHITS to DICOM RT dose data. The converted RT dose data can be read by conventional DICOM software so that you can set ROI and calculate DVH for further analysis. RT-PHITS is included in the PHITS package. In next several slides, we will introduce practical applications of PHITS to medical physics, and the first one is the applications to particle therapy. Since PHITS is the first general-purpose particle transport code that can treat heavy ion reactions, it has been extensively used in dosimetry for carbon ion therapy, particularly for secondary dose estimation. In addition, owing to the microdosimetric function, PHITS has been used for the relative biological effectiveness RBE weighted dose estimation by combining with the microdosimetric kinetic model. Next one is applications to BNCT, boron neutron capture therapy. BNCT gets growing attention particularly in Japan, and two treatment planning system for BNCT, Tsukuba Plan and NuCure, were developed by Tsukuba University and Sumitomo Heavy Industry, respectively, and the latter has been already approved by PMDA, Pharmaceuticals and Medical Devices Agency in Japan, and used in several hospitals for practical use. In addition, PHITS has been used for microdosimetric studies for BNCT, such as dose analysis in cellular scale and estimation of its therapeutic effect. As an example of applications to nuclear medicine, PHITS-based application for radionuclide dosimetry in meshes named Paradigm was developed by Memorial Sloan Kettering Cancer Center and open to public for free. It can automatically generate PHITS input files based on mesh phantoms by supplying the concentration of RI in each organ, and visualize the calculated dose distribution in ParaView, like this. In addition, the small target dosimetry is very important in nuclear medicine because doses are highly heterogeneous in microscopic scales in the case of alpha and low-energy beta emitters. So, PHITS was used in calculating S-values for cellular and tumor metastasis scale targets. As for the applications to diagnostics, PHITS was used in the development of web-based system for evaluating patient organ dose in CT exposure, named WASA-IRI. In this development, X-ray spectra of various CT machines are precisely reproduced and irradiated to Japanese voxel phantoms with different anatomies in PHITS. Using this software, you can easily calculate the organ doses by selecting the type of CT machine and phantom, and shooting range, without performing PHITS simulation. Approximately 2,000 facilities have been used for calculating their CT patient doses. Radiological protection is also an important application field of PHITS. For example, PHITS has been used in the calculation of dose conversion coefficients for various exposure scenarios, and the results were used in their evaluation by ICRP and compiled in 3 ICRP publications. Re-evaluation of atomic bomb survivor dose using J-45 series phantoms, which were constructed to precisely reproduce the anatomy of Japanese in 1945, is also an important application. It was found that the differences between new and old systems are up to around 15%, and these results are to be used in epidemiological study in future. The last application in this category is DNA damage estimation, which is important for both medical physics and radiation protection. Owing to the implementation of track structure mode, PHITS can determine the spatial patterns of each ionization and excitation in nanometer scale. Then, we developed a special user-defined tally for analyzing the cluster of the events within 10 base pair of DNA to identify the double-strand break DSB and cluster damage, and output the data in standard DNA damage (SDD) format. In addition, PHITS has been used for the RBE estimation of DSB yields for neutrons and X-rays. These applications are rather new, and more progresses are expected in the future. Next application is to space research. There are 2 useful functions for space research in PHITS. One is the cosmic ray source mode and the other is the dose equivalent estimator, which is commonly used protection quantity in space. Applicable particle types of the cosmic ray source mode in PHITS are galactic cosmic ray, so-called GCR, in space, and those in the atmosphere including secondary particles, and solar energetic particle in space for 5 historically large events. It can be easily used by specifying the time, location, and energy and angular ranges of users' interest. Then it reproduces the cosmic ray environment for the condition, like this figure. As for the dose equivalent estimator, conversion coefficients for dose equivalent for adult male and female are implemented. In addition, direct calculation of dose equivalent by weighting the QL relationship on dose is feasible. Next a few slides, we will introduce the space applications of PHITS, and the first one is the astronaut dose estimation. In last 2 decades, several space agencies conducted the Matryoshka project, which measured doses inside human phantom mounted on International Space Station including JAXA's Kibo module, and PHITS was used in the verification of experimental results. Next application is the estimation of cosmic ray fluxes in the atmosphere, which is necessary for various purposes such as estimate of the effects of cosmic ray exposures on human devices and the Earth, and design of cosmogenic nuclide dating and muon radiography. When high-energy cosmic ray are incident to the atmosphere, they cause cascade of nuclear and atomic interactions, so-called air shower. PHITS was used in this air shower simulation for various conditions, and the results were modeled to instantaneously predict the cosmic ray fluxes anytime and anywhere in the atmosphere. The model was named Palmer, and it is implemented in PHITS as the generator of cosmic ray source mode. In addition, an Excel version of Palmer named XPAX was developed, which is freely available from its website. Palmer XPAX are used in various research fields including geosciences such as cosmoclimatology. Next application is to the estimate of solar flare impact. There are 2 important studies in this field. One is the development of WARSAVIS, which represents warning system for aviation exposure to solar energetic particles. It can determine the cosmic ray doses at flight altitudes during large solar flare in real time, using the satellite and ground observations. In this development, PHITS was used for analyzing the air shower induced by solar particles. WRSA-VIS is currently operated by Space Weather Forecast Center of NICT. The other is the investigation of the impact of solar flare on planetary habitability. If a star can cause extremely large solar flare, its planet might be inhabitable due to the radiation effect, as we analyze the maximum radiation doses in the exoplanetary atmosphere using PHITS. Lastly, we will introduce other applications. Detector design is another important application of PHITS, and there are two useful functions for that purpose. One is the consideration of detector resolution and the other is sinful QMD mode. As for the detector resolution, PHITS can consider Gaussian distribution with Fano factor as expressed by this equation. In addition, user original function can be defined for expressing the resolution. For example, the response of cadmium-zinc tellurium detector can be calculated by PHITS with consideration of the asymmetry effect. On the other hand, sinful QMD is one of the most widely used programs for calculating the response of organic scintillator. It has high-precision neutron-carbon interaction database and conversion table from deposition energy to light output. Implementation of them into PHITS enables the calculation of response function for complicated geometry and source definitions, which cannot be realized by the original sinful QMD code. Next, we will introduce two applications of PHITS to detector design. The first one is the microdosimetric DZ model, which can universally determines detector responses for different radiation qualities such as ions and photons based on microscopic dose, Z, instead of LET, and the microdosimetric function in PHITS plays an indispensable role in this model. This graph shows the response of TLD for various ions as a function of LET, and the microdosimetric DZ model can reproduce its ion species dependence very well. The other application is to the design of ion beam imaging system based on pinhole X-ray cameras, which detect secondary electron bremsstrahlung produced by the primary ion beam. In this design, precise estimation of SEB spectra is the key issue, and delta ray production and activation calculation functions in PHITS play important roles. Next application is to the material science. PHITS has tally for scoring dPa, which is the average number of displaced atoms per atom of a material, so it can be used as the index of radiation damage. dPa tally in PHITS can score not only conventional index so-called nRT dPa but also newly proposed index, ARC dPa, considering the defect production efficiency of each material. This graph shows the dPa depth distribution in tungsten irradiated by 800 MeV proton. As you see, the new index, ARC dPa, is much smaller than the conventional dPa, indicating less damage are given to the material as previously expected. Next application is to device engineering. PHITS has been used in the estimate of soft error rate of semiconductor, where the information stored in semiconductor memory is flipped by incident radiation through the energy deposition process, and it is known that cosmic ray neutron is the dominant contributor to SER at ground level. So, event generator and cosmic ray source modes are indispensable for this estimation. Two PHITS-based SER estimators were developed based on device simulator and MSV model, which are accurate and fast, respectively. Using these methods, shielding effect was investigated by calculating SER in a fifth-floor concrete building, and found that neutron-induced SER is dramatically reduced by concrete shielding, and muon contribution to total SER is not negligible inside the building, up to 10% at first floor. The last applications introduced here is to severe nuclear accident. After the Fukushima nuclear power plant accident, large areas were contaminated by radioisotopes, and Giant developed software to evaluate the decontamination effect, named CDE. In this development, PHITS was used to make database of ambient doses in contaminated environment. Decommissioning of nuclear power plant is also important task, and estimation of radiation dose distribution inside it is indispensable. PHITS was used to predict most probable dose rates by fully reproducing the geometry estimated based on the internal investigation results. Lastly, we will give summary of this presentation. Important features of PHITS are the capability of transporting nearly all particles over a wide energy range in any materials, user-friendly interface and graphical output tools such as Angel and Big 3D, and sophisticated reaction models and libraries such as JQMD, Jindal with event generator mode, and track structure mode, and useful functions and tools for various purposes such as RI and cosmic ray sources, RT-PHITS, and microdosimetric function. Owing to these features, PHITS has been used in more than 50 counties, and the number of registered users increases approximately 1,000 per year. More information are available from our websites. Official website in Jaya is used for major update and tutorial announcements, and sending confidential questions and bug reports to PHITS office. Facebook page is more frequently updated for the announcement of bug and tips, so please press like if you want to get more casual information about PHITS. PHITS Forum is the user communication site for trading question and answer, and we recommended to use this site rather than the official website if you have any technical questions. In YouTube, there is a promotional video of PHITS, as well as tutorial contents including this presentation. That's all, and thank you very much for watching this movie. We hope to see you in either online or in-person PHITS tutorial soon.